Shallow groundwater affects low-lying coastal regions, which are host to the largest concentrations of urban development on Earth, with an estimated 1.8 billion people exposed to flood risk. This will be further exacerbated by climate change, as sea level rise causes more severe flooding, coupled with rapid urbanisation. Groundwater flooding is flooding from below, where groundwater emerges at the surface, and the controls on groundwater flooding are poorly understood. Hazards associated with groundwater flooding include damage to infrastructure, such as inundated pipes, roads eroded from below, increased liquefaction vulnerability, and health issues arising from dampness. Additionally, it can compromise septic systems and landfills, spreading contaminants through local aquifers. We need to study the system as a whole to understand how sea level rise, groundwater rise, and heavy rainfall work together, because their combined effects will likely overwhelm our drainage systems, leading to flooding. Yet, despite its growing importance, we lack a method to monitor shallow groundwater accurately over large areas and in real time. I propose to break down the wall of hidden groundwater flooding hazards by utilising existing fibre optic telecommunication networks combined with distributed temperature sensing. This shoots lasers down fibre optic cables and, based on the backscattering of the return light, provides temperature measurements along the entire cable at a high spatial resolution. For my PhD, I have been using this method to quantify flow beneath braided rivers. However, there was great difficulty involved with installing the cables beneath the ground. So by repurposing existing unused dark strands of fibre optic telecommunications networks would have significant cost savings, and extensive networks already exist globally. I will combine this method with distributed acoustic sensing, enabling the fibre optic cables to be used as vibration sensors. And this could provide continuous real-time temperature and strain data at a high spatial resolution across large distances. This solution would provide real-time monitoring of shallow groundwater dynamics, revolutionising groundwater monitoring and informing flood forecasting. This will allow for councils to predict groundwater flooding for development planning purposes and to monitor existing infrastructure for predictive maintenance. By repurposing our existing fibre optic networks, we're creating a cost-effective, scalable system to safeguard our cities and communities against an often overlooked threat. Thank you.
Thank you, Alice. Jury, any questions for Alice? Veronica?
Yeah. First of all, thank you for going first. That's a right thing. I just wanted to, one question for me to draw the link between the measurements you take,
yes,
so temperature and vibration,
yes,
to the actual what we understand about the groundwater movement.
Yes.
For the flooding, it must come up, and how can you read from the data you gather whether there's a rise or expansion or something?
Yeah, so for my PhD research, where I have fibre optic cables installed below a braided river, you get a different temperature signal where the ground is saturated versus unsaturated. And we're also hoping to be able to use the distributed acoustic sensing method to delineate basically, the extent of the saturated ground. Yeah.
Thank you.
Yeah, thank you.
Any further quick questions? Rich?
Thank you for your presentation. I'm interested in how you might use this idea beyond New Zealand. So, as you know, in the Pacific, we
yes,
have a climate issue and low-lying islands. So how might this idea be used in that context?
Thank you. Yeah, well, I would love to firstly use Christchurch as a case study, given there's extensive areas with shallow groundwater being above the depth of the fibre optic telecommunications networks, and first come up with a bit of a methodology for this method and acquire a machine, and then take that and apply that to the Pacific nations. Yeah.